Hi, welcome to Physics with Ms. Dahlberg. This is our lesson on kinematics. And kinematics is the study of motion. Motion is foundational to understanding every other unit because the concepts will be explained by how the objects move. So let's get started. So if you could see an overhead view of Dorothy and Toto walking down the yellow brick road, and this represents Dorothy, and this represents Toto, who traveled farther. If you said Dorothy, you're correct. If you said Toto, you are correct. And so the reason is that farther is maybe not specific enough. So let's define a few terms that we're going to use this year. So if we talk about the word distance, we're going to define the symbol for distance is D. And we're going to define it as path length. Path length, I got that L there. And so if distance is path length, in other words, if you follow the path that someone takes and you straighten it out and measure that length, that's the distance. Displacement, however, is the length from the starting position to the ending position. And so if we look at that, let's go back to Dorothy and Toto and look at those and see who had the bigger distance and who had the bigger displacement. So if we start with Toto and we follow Toto and look at Toto's path length or distance, if we straighten out this windy path, Toto definitely had the larger distance. Because if you look at Dorothy, the distance is just this straight line from where she started to where she ended. But if we look at displacement, and we'll do displacement in green, Toto started here and ended here. So from the starting point to the ending point, compared to Dorothy, starting point to ending point, Dorothy had definitely had a greater displacement. And so if we think about that, in terms of distance and displacement, we could put Toto over here for distance and Dorothy over here for displacement to kind of remember those two. And so if we talk about displacement, the symbol for displacement I will give to you, but first let's get the symbol for position. So if you are looking at a treasure map and you want to mark the position of the treasure, you would put an X. And displacement is the change in position. And so if we look at displacement, that is delta X is our symbol. And the delta we'll use a lot this year. The little triangle symbol is the Greek symbol delta, and it means change in. And whenever we do change in anything, we're always talking about the final position minus the initial position. And so final minus initial position will give us displacement. And so to define those two further, we need to define these two words, vector and scalar quantities. So a vector quantity is a quantity that has direction and magnitude. And a scalar quantity is a quantity with only magnitude. And you may be wondering, what does magnitude mean? And so magnitude, when we're talking about the magnitude, we just mean the size or the amount of that quantity. For example, for a scalar quantity that only has magnitude, we could be talking about 5 kilograms. And so 5 would be our magnitude. Another example of a scalar quantity could be like 5 feet or meters, 5 meters. We'll do 5 meters. If we look at vector quantities, we have to have both direction and magnitude, and those are very important. And so instead of saying just 5 meters, we would say 5 meters to the right, or north, or up, or down. And so direction is important for vector quantities. An example of that, you are probably watching this video during hurricane season. When we track a hurricane, we care about its speed a little bit. We care if it's going 5 miles an hour or 20 miles an hour, but much more important, we care about the direction. Is it headed toward us? And so when they report the information, the velocity of a hurricane, they always report the direction. And so that is a vector quantity that you are seeing on the news when you're reporting that. So going back to these two, Toto's direction never mattered for his distance. And so distance is a scalar quantity. Displacement, however, we care about where the ending position lies compared to the starting position. And so if we're looking at displacement is definitely a vector quantity. So displacements will always have direction. And so let's kind of look. I want to show you this little video from a movie you may have seen in your youth.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
So whenever you watch kids' movies, they always threw in a little tidbit for the parents, and hopefully you can get Vector's name joke. So Victor instead of Vector, he solved crime with both direction and magnitude. So we'll be talking about vector and scalar quantities all year. Today we're going to continue talking about the difference between speed and velocity. And one of these is a vector quantity and one of these is a scalar quantity. And so if we look at average speed, the symbol for speed is S, and speed is distance, and the symbol for distance is D, and it's distance over time. And so if we look at speed is a scalar quantity. How could you guess that speed is a scalar quantity? If you know that distance is scalar, then you know that speed is also scalar. And so if you look at the total distance over a period of time, that gives you the average speed. And so you might see average speed with a little bar over the top. And so average speed is what you might report for your trip to grandma's house. If you went 50 miles and it took you an hour, 50 miles per hour was your average speed. However, you may have gone faster on the interstate than you did when you turned off the interstate and you were sitting at stop signs. And so you report the average speed when you talk about your total distance over time. Your average velocity is a vector quantity. And if we talk about velocity, velocity is displacement over time. And so the symbol for velocity is a V, and the symbol for displacement was delta x, and the symbol for time is t. Now, if we look at average speed, the unit of speed is the SI unit is meters per second, but it could be miles per hour. It could be inches per century. It could be any unit of distance over any unit of time. And for velocity, the units are the same. Again, the SI units are meters per second, and you could do miles per hour, or you could do kilometers per year. And perhaps that's how glaciers move, kilometers per year or kilometers per century. And so the key difference in these two equations are the way we report the length. One is distance, which is path length, and one which is displacement, which is just the change in position from the starting to the ending. We don't care about the path. And so let's test your understanding with Fred and Frank. And so here on a grid, we have marked Fred and Frank's trips, and each square is only 1 meter wide. And so let's talk about the distance versus displacement versus average speed and velocity of each of those guys. And so go ahead and pause and write down the distance, displacement, speed, and velocity of both. Go ahead and look at that and figure out, and then we'll go over the answers. So if we're looking at Fred, let's look at Fred first. So Fred starts at A and ends at B. And so if we want to know the distance, we would follow Fred's path length. And so Fred's path length would go down 6 blocks, to the right 3 blocks, and back up 6 more blocks for a total of 15 blocks, and each block represents 1 meter, and so 15 meters. Fred's displacement, however, if we look at displacement, we want starting point to ending point, and so his displacement is 3 blocks or 3 meters, and to the right, or in this case, to the right, if we think of it as north, south, east, and west, would be east. Okay. And so going over to Frank, let's look at Frank's distance and displacement. And so if we look at Frank, Frank traveled up 3 blocks, over to the right for 6 blocks, and then down for 3 more blocks, for a total of 12 blocks or 12 meters, if each block represents a meter, for his distance, if we follow his path length. But his displacement, if we start at A and end at B, if you count the blocks, there are 6 meters here. And Frank also travels to the right, in this case, which is the east. And so let's look at our speed. How do we find average speed? And so if we try to find speed, speed equals distance over time. If we look at the total distance traveled by Fred, Fred traveled 15 meters. How long did it take Fred to travel that distance? Well, if you add up 4 seconds plus 3 seconds plus 3 seconds, you get a total of 10 seconds, or a speed of 1.5 meters per second. If we look at Frank's speed, Frank's distance was 12 meters. Frank's time was 5 seconds plus 5 seconds plus 2 seconds, or a total of 12 seconds, which gives us 1 meter per second for Frank's average speed. So Fred definitely went faster than Frank if you talk about speed. So let's talk about velocity. So for velocity, velocity is displacement over time. And so if we look at displacement, well, he traveled 3 meters east, if we're talking about displacement. And how long did it take him to travel 3 meters to the east? 10 seconds. And so if we look at the average velocity of Fred traveled 0.3 meters per second to the east. Capital. Okay. And was Frank faster? Well, if we look at velocity, I don't know. His speed was not, but was his velocity. So again, if we do displacement over time, Frank had a larger displacement. Frank's displacement was 6 meters to the east, and his time to do that was 12 seconds. And so if you look at that, he had a velocity of 0.5 meters per second to the east. So although Frank's speed was not as great, his velocity was greater. Okay. And so let's answer another question about Fred's trip. And it says the first thing Fred did was go south for 4 seconds. And so we're kind of looking at this part of the journey right here. If he wanted to cut his average speed in half, how long should that southward motion last? Okay. And so if we look at speed, speed is distance over time. And if we look at Fred's original distance of 15 meters and original time of 10 seconds, he had a speed of 1.5, but if we wanted to cut that in half, we would either need to half the 15 meters or double the denominator, the time. And so since we are changing how long refers to time, then we need to double the time. And so to get half the speed, we are going to have our original 10 seconds plus another 10 seconds to get, instead of 1.5 meters per second, 0.75 meters per second. And so if we do that, the time for the first leg would be our 4 seconds plus 10 more seconds for a total of 14 seconds. And so that's how we would half the speed. Now here's our follow-up question. Would this also half the average velocity? So if he had the same trip, he just took longer, in fact, twice as long, he didn't change his displacement at all. His displacement was still 3 meters. And so if we look at that, if we double the time and make that 20 seconds, you do indeed half the velocity. So yes, the velocity is definitely cut in half. And so instead of 0.3 meters per second to the east, he is 0.15 meters per second to the east. So definitely cuts the velocity in half. Why? The change in position is the same, but the time doubles. Okay. And so let's talk about, we talked about average velocity, and now let's talk about instantaneous velocity. And so instantaneous velocity is the velocity at any instant in time. And so if you look at your trip to school in the morning, on your way to school, you have a lot of different instantaneous velocities. There are times in your trip where your instantaneous velocity is 0 because you're stopped. There are times when your instantaneous velocity might be 35 miles per hour when you're in the school zone. It might be 55 miles per hour when you're on the highway. It might be 10 miles per hour when you're in your neighborhood. And so your instantaneous velocity may be very different at every point in your journey. But if you take the total displacement divided by the total time, you get your average velocity. So applying what you know to speed, about instantaneous velocity to instantaneous speed and average speed, can you answer this next question? What does a speedometer in your car measure? Does it measure average speed, instantaneous speed, average velocity, and instantaneous velocity? So the speedometer does not measure velocity. Why? Because velocity is a vector quantity with both magnitude and direction. And your speedometer does not tell direction. And so it's not B or D. So it's either going to be A or C. And your speedometer tells you your velocity at any moment in time, or your speed, sorry, at any moment in time. So that gives you your instantaneous speed. Okay, so now we're going to talk about acceleration. And acceleration, I want you to think about what is your definition of acceleration, because acceleration is one of those terms that you have an everyday definition of, but we have a very specific definition of in physics. And so how do you know if you're accelerating? Well, if you're accelerating, you could be speeding up. You could be slowing down. But there's one more thing you could be doing. You could be turning. And so if you think about that, these are all things that you feel when you're in your car. What happens to you when you step on the gas and you speed up? Your body goes back against the seat. What happens when you slow down? When you slam on the brakes, your body goes forward away from your seat. And when you're turning, your body goes in the opposite direction of the turn. And so you feel accelerations. So what are you changing in all of those situations? You're changing your velocity. So how do you know you're not just changing your speed? Because turning is also part of that. And velocity is a vector, and direction is important with vector quantities. And so if you change direction, even if you don't change your speed, in fact, you could have your car set on cruise control and you're turning around a curve, you're accelerating, even though you go a constant speed the whole time. So if we talk about acceleration, the symbol for acceleration is A. And so we'll talk about acceleration. And so actually, let's do it here. Acceleration is defined as changing velocity, right? It's the rate of change of velocity. And so if we change velocity, and this is the change in velocity over a unit of time, we have acceleration. And so the rate of change of velocity. Now, the units of this, if we look at velocity, the units of velocity are meters per second. And if we look at time, the unit of that would be something like seconds. And so that gives us a really kind of weird unit of meters per second squared. And, you know, it might be hard. It's kind of hard for my brain to wrap around what is a second squared, but don't really think about it like that. This is, you're changing your speed, you're changing your meters per second every second. And so that's what this second squared means. So let's move on and talk about, here's a sentence that has acceleration, and we'll talk about what that means. So kind of Mad Libs style, if you've ever did Mad Libs when you were a kid. But a car's acceleration is 5 meters per second squared. That means that the car's velocity increases by 5 meters per second every second of time. And so if 1 second passes by, your car is now going 5 meters per second. If 2 seconds pass by, your car is now going 10 meters per second. And then 15 meters per second a second later. And then 20 meters per second a second after that. If we talk about acceleration, you see this in car advertisements. And so if you see a commercial where you see a car advertised as going from 0 to 60 in 2 seconds flat, when this happens, the car's velocity increases by 60 miles per hour every 2 seconds And so if we look at that, if the car's acceleration, if you speed up 60 meters per, or 60 miles per hour in 2 seconds, your acceleration is 30 miles per hour every second. So every second you're speeding up 30 miles per hour. Another way to write this might be miles per hour per second. Okay. Things that fall accelerate at 10 meters per second squared. So if you drop a penny from the top of the Empire State Building, the penny's velocity increases by 10 meters per second every second of time. Okay. So if you're looking at a diagram of speed, so right here, the velocity would be 0 meters per second. If it increases by 10 meters per second every second, 1 second later, the velocity would increase and it would be 10 meters per second. In the next second, it would double. So instead of this long, it would be double, and the velocity would be 20 meters per second. Okay. And so if we describe the difference between velocity and acceleration, you could define these as rate of change of what? And so go ahead and define those. Velocity is the rate of change of position. And acceleration is the rate of change velocity. Okay. Now, let's talk about graphically what this would look like. And so we are going to look at different motions like standing still, moving forward at a constant velocity, and so forth and so on. And these are different graphs. So x versus t will be a position. Position versus time graph. This is a velocity versus time graph in this column, and these are acceleration graphs. Okay, so if we have an object that's standing still, what would a position time graph look like for that object? And so we can do that. I'm going to do this in green. Where is its starting position? I don't know. So I'm going to pick one. I'm going to say it starts off right here, but it could be anywhere along this axis. The starting position wasn't defined. And if it's standing still, it doesn't change position. So as time moves on, the position is constant. And so there is a straight horizontal line on the position time graph. Now, if something is standing still, its velocity is 0. And so right here on the velocity time graph at 0, we would have a horizontal line at 0. And if something is standing still, its velocity is 0, and that velocity of 0 is not changing, and so therefore there's no acceleration. So let's move on to something moving forward at a constant velocity. And so if I have a starting position, and it doesn't matter where I pick, I'm going to start at 0. If you're moving forward at a constant velocity, forward is considered the positive direction, and your graph would look like this. Now, if it had a constant velocity, this velocity would be constant, and so it would have some kind of positive velocity. And where could we find the velocity? The velocity would come from the slope of this line. As you know from the buggy lab, the slope of this position time graph gives you the velocity. So if you have something at a constant velocity, you know that the acceleration is constantly 0. To have any kind of acceleration, you must have a changing velocity. Now, I could have started this original graph here or here, and the velocity and acceleration graphs would be identical. Okay, now let's do moving backward at a constant velocity. If you're moving backward or in the negative direction at a constant velocity, you start at one position and you end at a more negative position. So if you start here, you end maybe in a more negative position. And if you move at a constant speed, you have a straight line for this graph. And so if we have a straight line, we know that this this graph, the slope of this graph gives us the velocity. And so if the slope of this graph is negative and constant, our velocity is negative and constant. So we have a horizontal straight line for the velocity graph. Now, if there is no change in velocity, meaning this is like a -2 and it's always a -2 velocity, then there is no acceleration. So we have a 0 on the acceleration graph. So now we're speeding up in the positive direction. And so if we're speeding up, let's say we start at 0, and if we're speeding up, what would that look like on this kind of graph? Go ahead and make a prediction. So instead of moving at a constant speed in the positive direction, we are going to move slowly at first and then faster and faster. So you see this kind of curve opening upward parabola, or kind of a happy face. And so that is speeding up in the positive direction. Now, if we look at this, if we have a velocity that's in the positive direction, we're going to find it on the positive side, and it's going to increase. And if we look at this, our velocity graph will look something like this. Now, how can you tell? What's another way to look at this and tell that this is what the velocity graph will look like? Well, we know the slope of this graph gives us the velocity. So we can find the slope of the tangent line at various points in time and see that it gets more and more positive. So if we draw a tangent line to this curve at 3 different points, if you look here, it's pretty close to 0. Right here, we have a slope of, say, maybe 1. And here, the slope is bigger, so we have a slope of perhaps 2. And so our velocity goes from 0 to 1 to 2 at those different times. Now, if it has a changing velocity, it definitely has acceleration. And if it has an increasing velocity in the positive direction, it has a positive acceleration. And this graph, if we look at the slope of the velocity time graph, if we find the slope and it is the rise over the run, or velocity, the change in velocity over the change in time, well, this is the definition of acceleration. And so the slope of this graph will tell us the acceleration. And since this has a positive slope, it has a positive acceleration. Moving on to slowing down in the positive direction. So if we start here, and if we're slowing down, that means our displacement is less and less as time goes on. So it doesn't matter where we start, but if we start at 0, that means we're traveling farther in the beginning and not as far in the end. And so our graph will look something like this. And if we want to figure out what does the velocity look like when we are slowing down in the positive direction, the slope of this position time graph will tell us the velocity. So let's look at the slope of this graph is changing. And so we'll look at the slope in 3 different parts of the graph. So if we draw a tangent line to the curve, at this point right here, the slope is pretty close to 0. And so we can say at the end, the slope is 0. Right here, the slope it's positive, but it's not very big. So we can say this is like 1. Oops. So we can say this is 1. And this slope is positive, but steeper than this one. So we'll give it a value of something like 2. And so if we come over to the velocity graph, we can say this is 2, 1, and 0. And so our velocity goes from initially a very high positive velocity, and then down to 0 eventually. Now, if the slope of a velocity graph tells us the acceleration, what is the slope of this graph? The slope of this graph is constant and it's negative. And so we could look up and figure out the exact value, but we know our acceleration is going to be constant and negative. And so if we look at the slope of this graph, that will tell us the acceleration. So now we can go to speeding up in the negative direction. So if we're moving in the negative direction, we would start at a positive value and end at a negative value. And if we're speeding up, that means we're going to travel faster and faster as time goes on. And so our graph would kind of start out not changing very much and then change more dramatically. And so we have something that looks like that. Now, if we're moving in the negative direction and speeding up, and we want to know what's happening to our velocity, since we start away and end in a more negative position, it's always going to be negative. So we're always traveling in the negative direction. And so if we look at the beginning, we're not traveling very fast, and then we're going pretty fast in the negative direction. So our velocity graph will do this. Now, if you want to look at this and kind of analyze it, the slope of our position time graph gives us our velocity. So let's draw some tangent lines and find the slope of these tangent lines. And so if you look at the beginning, the slope of this line is 0, therefore the velocity is 0. Then the slope changes, and as it changes, it becomes negative and a little more steep. And so this would be like -1, and here it's negative, but it's even steeper. So this could be like -2. And so if we look at those other two times, this would be like -1 and -2 for the velocities. And so this is how this velocity graph matches the first one. Now, if we look at our acceleration graph, if we are speeding up in the negative direction, that's considered a negative acceleration. And if we look at the slope of this line, it's constant and it's negative. And so we have a graph that looks something like this. Constant, and this should be a straight line, a constant negative acceleration. Okay, and for our last graph, which is missing the position time graphs, so we'll add them really quickly. Our last graph is something that is slowing down in the negative direction. And so if we graphs, position time graph of something that's slowing down in the negative direction means it starts away from 0 and ends in a more negative position. And if it's slowing down, that means it's moving really quickly at the beginning, and then it's not changing as much. And so our graph will look like this. And so it's changing pretty quickly to not changing very much. So if we want to do a velocity graph of this, we would start out, if they're moving in the negative direction the whole time, we're going to stay in the negative velocity. And if we draw some tangent lines to figure out what's happening to our velocity, well, our slope is pretty steep and negative, getting less steep and then approaching 0. And so if it's a very negative velocity, it would start here at the most negative value and then slowly go to 0. And so what would our acceleration look like? Well, oddly enough, if you are both slowing down and moving in the negative direction, that correlates to a positive acceleration. And so if you look at this graph, the slope of the velocity graph gives you the acceleration. The slope of this line is constant, and it's also always positive. So it always has a positive slope. Even though it's in the negative quadrant, the slope is positive. And so the slope tells us our acceleration. So the slope is positive and constant. The acceleration is positive and constant. And so I would like for you to look at those graphs and see if you can figure out some patterns and rules. For example, when the velocity is positive, what does the position graph look like compared to when the velocity is negative? And so let's look at that, see if you can come up with a rule. And if we look at this, here we have a position graph where we're moving forward, moving backward, moving forward, positive direction, moving forward in the positive direction. These two were moving in the negative direction. So did you notice this pattern? That when the velocity is positive, the position graph always has a positive slope. And the converse is also true. When the velocity is negative, it always has a negative slope. So go back and look at those graphs and see if you notice that pattern. Positive slope, negative slope, positive slope, positive slope, negative slope, negative slope. So it's like -0, -1, -2. Okay. What about this? When the acceleration is positive, what does a position graph look like? When the acceleration is negative, what does the position graph look like? When the acceleration is 0, what does the position graph look like? So let's look at those acceleration graphs and see if we can notice a pattern. So these first three have an acceleration that's 0. What is the same? If you look at these, the position graph is a straight line. So if acceleration is 0, the position graph has a straight line. A straight line. But what about positive and negative acceleration? What do those look like? So if we go back to all of these that have acceleration, so this one is where it starts compared to all of these. So some of these have a positive acceleration, some of these have a negative acceleration. What's the same? They all have curves. Tell me about the curves. So here we have a positive acceleration, and here we have a positive acceleration. Tell me about this curve and this curve compared to our two negative accelerations, the two in the middle, this curve and this curve. So did you notice the pattern that when the acceleration is positive, the curve, which is a parabola, opens upward? And I always like to think of it as positive acceleration has a position time graph with a happy face. Positive always, refers to happy. So the curve, the parabola in those graphs open upwards. If we look at the acceleration graph, the curve opens downward. And so you always notice on the negative accelerations, you notice a frowny face. So you have a little frowny face there. Let's go back and look at that. So the positive acceleration, I have half a smile. Down at the bottom, I have the other half of the smile. For the two negative accelerations here and here, I have a downward open and parabola, a downward open parabola, half of a frowny face. Okay. How about this? When the acceleration is positive, what does the velocity graph look like compared to when it's negative? Or what about when it's zero? So let's start with when it's zero, because those are the first three. What does the velocity graph look like compared to the rest? So when the acceleration is zero, did you notice that the velocity graph has a horizontal straight line? What's the slope of a horizontal straight line? If we look at that, the slope of a horizontal straight line is always zero. And so the slope of the velocity graph is zero. If we look for positive acceleration, let's look at our two graphs with positive acceleration. Tell me what you notice on the velocity graph. If you have a positive acceleration, the velocity graph has a slope that is positive. If you have negative acceleration, the velocity graph has a slope that is negative. So those are patterns that you're looking for. So here's the last one. When the object is speeding up, tell me about the acceleration and the velocity. So going back, look at the two instances where we have speeding up. So we have speeding up in the positive direction and speeding up in the negative direction. If you look at speeding up in the positive direction, the velocity is positive, the acceleration is positive. If you're speeding up in the negative direction, you have negative velocity, you have negative acceleration. The signs match. The opposite is true for slowing down. If we look at slowing down in the positive direction, we have a positive velocity because it's on the positive side of the quadrant for velocity, and we have a negative acceleration. If we look at slowing down in the negative direction, we have a negative velocity and a positive acceleration. So the signs of acceleration and velocity match if they're speeding up. The signs of acceleration and velocity are opposite. So one's positive and one's negative if we are slowing down. And so those are a few things to notice as we approach these graphs. So